All right, so continuing with the stuff you got to know for the exam, the next major topic we covered was Henselslemma, right? So Henselslemma allowed us to solve polynomial equations by prime powers, right? So to solve f of x, I have to hold this at the right angle, f of x is congruent to 0 mod a prime power, p to the n. P is like always a prime whenever I write the letter p, unless I say otherwise, which I never do. So here f is a polynomial with integer coefficients, because like everything is always with integers unless you say otherwise. To solve this, you first solve f of x is congruent to 0 mod p, and then you lift solutions, right? Every solution to this equation, mod p to the n, for some higher n is by definition a lift of a solution mod p, right? Just reduce everything mod p. Right, but it actually tells you how the lifting works. So you find the solutions mod p, often by brute force, unless you know a better method. We know a better method now for degree 2 polynomials. There exist similar methods for higher degree situations, like the higher versions of quadratic reciprocity. So that is actually possible, but we usually just do it by brute force because we have small enough primes, small enough polynomials. And then you basically, well, we've talked quite a lot about this, and I think, well, based on the performance of the exam, it seems people have really nailed this. But right, you look at whether you have simple or multiple roots. For multiple roots, you have to do a little more brute force check. For simpler roots, you have this formula that you have to know that tells you how to lift it just lifts from every prime power to every next one. And once you've done the pre-computation of how to lift it from p to p squared, the next computations are kind of plugging into the same formula with the same coefficients over and over, and you just have this machine for just producing answers. All right. And so this can also, of course, be combined with the Chinese remainder theorem. And so this is like the power of a lot of our results are not in isolation, but in how the different methods combine, right? And so that's part of the aspect I take the focus on. I try to emphasize throughout the course, how do the different things fit together? I think the book does a little less of that. Like, I think there was even some exercises we did in the homework where they're like, you can combine the Chinese remainder theorem to solve some certain congruences together with reciprocity, to solve quadratic congruences mod not primes, and that was just kind of a small buried in the exercises, right? But I consider all of these things should always be considered in relation to all of the other theorems at all times whenever possible. So it's really important to have the big picture of idea of what these things are doing and what they can do for you. So anyway, with the Chinese remainder theorem, we can solve any polynomial is congruent to 0 mod any number m. Right? Because Chinese remainder theorem allows you to take any congruence mod m, turn it into a congruence with the fundamental theorem of arithmetic plus Chinese remainder theorem to a congruence mod p to the n. This allows you to turn any congruence into a congruence mod p if it's a polynomial congruence. And, well, that's kind of the end of the line for most situations, unless we're lucky, like unless we have a degree 1 or 2 polynomial, we just kind of have to use brute force. However, we also have one key fact, which is often useful. So there's a lot more special things about polynomial congruences mod primes, and the key one that we mentioned that I think is important to know is that f of x is congruent to 0 mod p. I don't know how many solutions it has in general, or you can't know, but it has at most degree of the polynomial many solutions, right? This is only true mod a prime. So it has at most the degree of f solutions mod p. All right. So for example, if you have a degree 3 polynomial and you find 3 roots by brute force, you found them all, so you can stop looking. So that's one way this key fact can save you some time in certain situations. And right, this stuff can all be combined as well. Of course, you can also solve systems that are not of the form x is congruent to something. You can also solve systems, as we've talked about, like ax, let's say a1, x congruent to b1 mod m1, through anx is congruent to bn mod mn, right? So you use Chinese remainder theorem plus the theory of linear congruences that we know, right? Each one of these equations can be reduced to a bunch of possibilities mod the mi, and then if you compare them all, you get branches into a bunch of possibilities. But each of the possibilities, either when you compare two moduli, if they're not relatively prime, you can't use Chinese remainder theorem. But fortunately, if they're not if two of the moduli that you get are not coprime, well, then either any two equations you compare where the moduli are coprime, either they're inconsistent, meaning there's no solution that satisfies both of them, or one of them implies the other, right? You can always break up into prime powers and then get all these deductions and build these big trees where you look and you trim off the branches of the tree and get to a system of equations that you can actually apply Chinese remainder theorem to. So just remember we did some of those examples. If it's been a while, you don't remember exactly how those go, that's a good example that you should review. All right? But I like these things, especially for final exams, that really require you to know what's going on in the class with the big ideas, and require you to use to really think and use multiple ideas at the same time. Okay? All right, so that was kind of the end of our big set of things of solving certain types of congruences for a little bit, and we took a little break after that. Right, so for Henselslemma, we also talked about this p-adic stuff that was a glimpse into further things. And again, that's not something that's really a core idea to what we're doing in this class, so that's not kind of exam type material. That's more of, we studied it because it's interesting and very important, but it's not part of our global picture for the final exam. It is part of the global picture of modern number theory, but we're not really getting far enough in that is part of our global picture of final exam type stuff. So after that, we studied local to global principle, which is a really amazing fact. It's really a motivational fact for much of what number theory is today. And it does actually matter in the real world if you care about cryptography and elliptic curve cryptography that your credit card uses when you swipe it on your chip. Actually, it's really important. But anyways, basically the really amazing thing that we learned is we could study any conic section. You can study any Diophantine equation that's basically degree 2 in 2 variables, and you could always find whether there's a solution or not using local to global, and then once you have a solution you can find all of them. And the motivating example that you do need to know, so local to global again is just for motivational purposes and not part of our global picture of this class, but in the midst of that we did something that you do need to know for the final exam, which is Pythagorean triples. All right, so again, you probably learned about these in high school, but it's a squared plus b squared equals c squared, right, where these are all integers. Okay, and the key idea of how to find them all, so the ancient Greeks knew how to do this. There's a one-to-one correspondence with the rational points. This is a homogeneous polynomial, as we talked about in the last couple lectures, all powers 2 here. So we can divide everything out by c. Well, forget the case c equals 0, that's just 0, 0, 0, it's kind of boring anyway. In all other cases, I can divide by the c and get a rational point on x squared plus y squared equals 1, which is the unit circle. Right? And then to find all points are just the rational Pythagorean triples correspond to rational points on the unit circle. And we have this point -1, 0. That's a particular point, right? This is the point. Local to global tells you whether there's a point like -1 to 0 to start with. Once there's a solution on any conic section, so it could be an ellipse, could be a hyperbola, whatever, then you can just take the rational points, actually just correspond to the rational slope. So you basically are parameterizing a circle by angles, right? That's like what you do with polar coordinates in calculus. But instead of using angles, I want to kind of respect rational numbers and integrality. So angles aren't really so good. They involve pi's and stuff. So I use slopes, right? So you look at rational slopes through a particular point, and this point is picked for convenience because, well, it corresponds to kind of this trivial solution, and the slope of the line that touches this circle at this point is infinite slope because it's a vertical tangent line. So when we talk about rational slopes, it actually doesn't show up in our parameterization, which is what we want. Right, but it's just one choice, and that leads to the idea of the primitive solutions, the primitive Pythagorean triples, right? That just means that the GCD of the 3 numbers equals 1, okay? So if you know all the primitive ones, you know all the Pythagorean triples just by rescaling, like under similar triangles, for instance, right? And the primitive solutions, there's a formula for this, a parameterization, and it's absolutely critical that you know this formula. I absolutely expect it on the exam. So the primitive solutions are those of the form m squared minus m squared, m squared minus n squared, 2mn, and m squared plus n squared, okay, where m and n are co-prime. No surprise there, otherwise it wouldn't have a primitive solution. You can see that right away. And also, as you computed on the homework, you need that m and n have opposite parity, right? So one of them's even, one of them's odd, right? And this produces this formula, as you range over all m and n satisfying these conditions, produces for you all primitive Pythagorean triples, all right? So that's a really key fact to know. The idea, you should know the general idea, like you did the problem of finding all the points on an ellipse, given that you knew one of them. You didn't need local to global to do that, just you need to know that there was a solution. And if you're handed one, you should know how to parameterize all of them by solving equations. Although, that formula is a little bit, the formulas you do are a little long for an exam, so probably I wouldn't ask that, but it would be fair game if there were time. But certainly this formula here, there are plenty of questions that one could ask that require you to know this formula to solve problems involving the triples, right? And for example, we just used that again in our proof of Fermat's last theorem for exponent 4. We used this once again. All right, so maybe this is a good stopping point because we're coming back to some of the other classical congruences again in what I want to review next.